In this video, we're going to talk about colligative properties. So colligative properties depend only on the concentration of solute particles present in a solution. And some of these colligative properties include vapor pressure reduction and boiling point elevation. And those are very related. We'll talk about that in a minute. It also lowers the freezing point of a given system, and it can lead to osmotic pressure. So we're going to go over those. First two, boiling point elevation and vapor pressure lowering. We know the temperature at which vapor pressure equals the atmospheric pressure is the temperature at which a liquid boils. Now, if we have pure solvent, meaning either water or some other liquid, pure liquid, we know that as you add energy to it, those solvent molecules are able to overcome the intermolecular forces holding them in place and essentially escape from the solution, from their system. And when they do so and they enter the vapor phase, they exert pressure just like any other gaseous molecules do. However, when you have solute particles dissolved, it essentially impedes that process of them escaping the liquid phase and going into the vapor phase. Thus, you would have less molecules in the vapor phase, lowering the vapor pressure, meaning you would need to reach a higher temperature in order for the vapor pressure to equal atmospheric pressure. And you can see that in this table right here. This shows atmospheric pressure, and this shows the temperature. And these lines represent the vapor pressure. In the green, it represents the pure solvent, and you can see that in the purple, you have a lower vapor pressure at a given temperature when you have the solute dissolved in it. Okay? So, like I said, this depends only on the concentration of solute particles. And not all solutes are the same. For example, something like glucose or a large covalently bound molecule, it's not going to break apart into more particles. It's going to stay that molecule of glucose the entire time. However, when you dissolve something like sodium chloride or any other ionic compound, it's going to break apart into more ions. So sodium chloride breaks into 2 ions, and calcium chloride would break into 3 ions because it's CaCl2. So when we're calculating the impact on the boiling point or the freezing point, it's going to be the delta T right there. We're going to have to look at something called the Vant Hoff factor, and that represents the number of particles that a given solute can break into. The more solute particles it breaks into, the more of an impact it has on the boiling point change. There's also going to be a constant for a given solvent. For example, water has a certain K value or constant value than, say, hexane or benzene does. So every solvent has its own unique constant by which that Vant Hoff factor will affect the boiling point. It also depends on something called the molality, which is slightly different than molarity. Molarity represents moles of solute per liter of solution. Molality, usually designated by a lowercase m that's italicized, is going to represent moles of solute per kilogram of solvent. So it's essentially a particle to mass of solvent ratio instead of total volume of the solution. So you can see that because it lowers the vapor pressure, it requires a higher temperature to get that vapor pressure equal to atmospheric pressure. And you can see over here that actually adding solute will lower the freezing point. So let's think about why that happens. When you're looking at something freezing, you have solvent molecules coming close to each other, losing energy, and their intermolecular forces being allowed to take hold. Well, if you have solute particles present, it's going to interfere with that process in allowing to form the crystal. So it's going to actually need to have a lower and lower temperature to actually lose enough energy that those solute particles don't interfere with the process as much anymore. So the vapor pressure gets lowered, the boiling point gets elevated, the freezing point gets lowered, and it can also lead to something called osmotic pressure. Now, osmotic pressure is represented by the letter pi. No, it's not 3.14159. You know what it is. Anyway, it's going to be equal to that same Vant Hoff factor, except this time it's multiplied by the molarity, the gas constant, and the temperature in Kelvin. Now, you're probably not going to have to do any calculations with this on the SAT, but what you need to get is the conceptual component of it. So the higher concentration for all of these of solute particles, the more of an impact those properties have on them. So anyway, here it shows in this U-shaped tube pure solvent on this side, and it shows on the other side a solution that contains both solute and solvent. Now, what's going to happen is, if you let this reach equilibrium, you're going to actually observe that the solution level will be higher on the side of the semi-permeable membrane, which only lets the solvent pass through. The water level will be higher than the other side, the solution level will be higher than the pure solvent. And so essentially, just like when we were reading manometers in the gas unit, that difference in height between the fluids is going to represent the osmotic pressure. Why you get this buildup of pressure on this side is because you have solvent particles flowing this way, and you have solvent particles flowing that way. The solvent particles flowing towards the higher side of the tube are unimpeded by solute particles. However, the solvent molecules going in this direction are going to be impeded, their path would be impeded by the solute particles in the way, and so it slows that rate. Thus, initially your rate of flow this way is going to be higher than that way until they end up reaching equilibrium. So it can result in some what we would call osmotic pressure. So those are colligative properties. They depend on the concentration of solute particles present in the solution, and we've talked about what they impact.